Hi everybody. Now this is the lecture for the sound intensity and its measurements. So what we're going to do is we're going to discuss all the properties pertaining to the loudness and how sound is measured. In fact, we're not so much of interested in the measurement itself, but rather how we can predict the loudness based on certain scientific principles. Okay, so let's get started. Now, as you all know, that amplitudes of sound is the physical measurements of what sound is. So far, we have covered, in fact, three aspects of sound. All right, and what is the three aspects of sounds that we have covered? Remember the three P's? We have P, production, propagation, and perceived loudness. So these are the three things that we have covered: production, propagation, and perceptions. Okay, during the productions of sound, sound is produced. So sound will have an amplitude as it produced inside. Now, as it travels to different mediums such as air, liquid, and gaseous state, and solid state, solid, we experience a few properties such as reflection, refraction, diffraction, so on and so forth. All right. So these are the properties of sounds that undergoes through all these things. Now, when it comes to the ear itself, all right. Okay, when sounds enter to the ear, it goes through the auditory canals to the eardrum, which is attached to three sets of bones known as the ossicles. Consists of hammer and nail and straps, and is the bones ends at the cochlea, which is a cell-like structure. All right, attached to it is the oval window. All right, on the other side, there is the sucker window. Okay, and within the cochlea itself, there is a basilar membrane. Use a different basilar membrane right down here in the center. Okay, so the basilar membrane consists of hair cell which sends electrical pulses all the way to the head, or rather all the way to the brain, where you perceive a sound. Now, under the perceptions, let's look at all the different measurements of sound in different phases. Now, during the productions of sound, the measurements of sound volumes is measured in terms of energy. A bit weird here. Energy. During the propagation itself is also energy. Now, once the uh, sound energy, or rather the enters into here, the energy is converted into electrical pulses. All right, electrical energy. Okay, and it's perceived by the nervous system how loud it is. So when it comes to measurement of energy, measurement of sound itself, during the production, the energy is measured in terms of joules. Here, same thing, joules, joules, and all the way until electrical signal, which when during the perceptions is measured in terms of forms. So that's the difference between the measurement of loudness at different phases. Today, we're going to discuss the energy or the intensity of an energy for the production and the propagation phase. These two. Okay, all right, so let's move on a little bit. So the amplitude of sound as the physical measurements of sound as of strength or weakness. So it's basically the displaced amplitude, in which down here you have the air particle being displaced up and down. So this is the displacement. the greatest distance that each packet of air move in either side of its normal positions. Of course, air don't move in transverse form. Air move in longitude. The energy is transmitted via longitudinal form. Okay, so where the direction of propagation is parallel to the directions of vibrations. Now, of course, there's also the velocity amplitude, which means how fast this displacement goes up and down. So this is usually measured by the gradient. And lastly, the amplitude of sound can be measured via pressure of the air. So the pressure of the air here is lower than the pressure of the air here. Of course, the rarefaction has a lower pressure of air because the air particles is spaced apart, whereas here the air particle is compressed, giving rise to high pressure. All right. Okay, so moving on next. Now, before we understand the intensity further, let us relate back to energy. In your secondary school, you learned that energy is the ability to do work. Now then, what is work? Work is something get done. But officially in physics or in science, work is defined to be the force multiplied by the perpendicular distance. Sorry, is force measured by the direction traveled in the direction of the force. Meaning, if I have a force here and I pushes an object here, the object should move in the directions of the force, and that constitutes work. So if someone is carrying something, okay, okay, is carrying something, and he is moving it, okay, he's applying force here. Just the act of carrying itself, when the force is here, with no distance move, it does not constitute any work done. Right? Okay. So, but if the person moves, the work done is done by the leg in pushing the load forward. No work is done in the process of carrying. Okay. So this you have to be very clear. Moving on next. So work is equal to force times the distance traveled in the directions of the force. So twice as hard is equal to twice the force. Twice the distance is twice 2 times the original distance. So if we have an oscillations, okay, that is proportional to the square of the amplitude, then this will give rise to a new relation. Okay, so what happened here is, imagine there's a spring down here holding on to the mass. And it's a resting position. Okay, so now what happened here is, if you were to add more weight here, the spring will stretch even further if the weight increase. All right, so the energy stored inside the spring, not the work done, the energy stored inside the spring is twice the energy stored inside here, because the weight increased by twice it, given that both are the same spring. All right, so now in a process of oscillations, or in the process of vibration, such as air particles and whatsoever, now the energy of the oscillation is directly proportional to the square of the amplitude, meaning the energy of the vibration is directly proportional, we use the symbol, to the amplitude square. Okay, so of course mathematically we cannot represent using the alpha symbol here, which is energy of the vibration can be represented by a constant k. This could be 1, could be 2, can be 1. It's just constant, no change. Multiply by the amplitude squared. So take note of this relationship that we have here. Okay, given an oscillation with amplitude A, we can write that the energy is equals to Ka squared. Okay, so now let's move on. Now, if a wave X have an amplitude of A and an energy of E, okay, we can rewrite it to be E is equals to K A squared. Now, what would be the energy if the amplitude were to increase by twice? So energy of Y is equals to K. Now it's 2 times the amplitude of A. Now knowing indices, what can we rewrite? We can rewrite this as K 2 squared A squared. Rearranging will be 2 to the power 2 is 4. So it's 4Ka squared. Now Ka squared itself is Ex. So it's 4 times Ex, the original of energy. Alright. Now next. Given that the new energy is twice Ex, what will be the amplitude? Alright, so let's say Ez is equal to twice Ex. Ez is twice Ex. Now, putting in the equation Ka square inside here, alright, we have something like this. Now we know that in order to put it in terms of A, we have to put everything inside here. Okay, so what we have here is this is square root 2 whole thing squared K A squared. Alright, knowing indices, you can rearrange this to be square root 2 A squared. So which means to say the new amplitude now is square root 2A. Okay, got it? So you have to rewrite mathematically in order to find out what's the new amplitude if we increase twice the energy. So what does this mean? Which means to say that if you are inside your logic or inside Audacity and you increase the amplitude of your wave by twice its original amount, so what would you expect? You expect that the energy would increase by 4 times. Okay. Now, if the energy increased by twice, so that means the knob you increase, and then you realize that you instead of 100 watts, you pump in 200 watts itself. Now, then what would be the amplitude? The amplitude simply just increased by square root 2. So this is the implication that we have in audio aspects. So as you can see, which wave is the strongest? I mean, which wave has the greatest amount of energy here? It is EY because it's 4 times the original of EX. Okay. Now moving on next to energy itself, we have this. So you see, this is the answer that we have down here. The working is shown in the previous slide. Now, energy. We are more interested in the energy of sound wave than its amplitude. No, we are more interested in the rate of energy transfer, which is the power. Okay, now here it goes. Although it says that sound or the sound seems to be producing a lot of energy, but energy is a concept that is calculated in its totality. Okay, an analogy to that is imagine a flow of water. Say, okay, imagine you have a water tank. Let me use the bamboo to illustrate to you what does it mean inside here. Okay. Energy is equivalent to a reservoir of water. It's just like you charge your portable battery charger, and the amount of energy that it can store is this much. All right, so this is energy. But when we use the energy to produce sound, what happens? We can, it is equivalent to the flow of water. So flow of water is as if it is equivalent to the power. How much water is flowing out in one go? It's as if you are charging your handphone, all right, and you have a cable that says, oh, 2.4 ampere, and some is 1.0 ampere, which means in 1 second, how much energy is it drawing out from here? Now, let me ask you a question. Would you prefer a higher ampere when you're charging your phone, or would you prefer a lower ampere when charging your phone? Of course, that depends. Now, many people would prefer higher ampere because the amount of energy get transferred from their portable device to their handphone, portable device to their handphone is much quicker, so that the handphone gets charged up faster. But of course, technically you should not charge your handphone so fast, as it will actually shorten the lifespan of your battery. Okay, now that aside, so energy is the amount of reservoir that the a device has, and the power is amount of energy that's flowing out in 1 second. That is power. So if energy is measured in terms of joules, then power is actually joules, number of joules per second, which is known as watt. Okay, all right. Now, in the music appliances, or you have a stereo, hi-fi, or whatsoever that is producing music. All right. Now, which means to say that, are you able to measure this in terms of energy? You can't, because you do not know how long you're going to play the sound for. If you're going to play the sound for 1 second, then you just measure the total amount of work done during that 1 second, and then you get the energy of the device. But when we are measuring device, we cannot measure in terms of energy, simply because we do not know at any point how long this device is going to play. And of course, it's not meaningful. How do I want to know the overall energy um, played by this device? Unless I want to check my power meter and see how much I need to pay to power up this thing. But most often, we want to see how loud this device can give when it's playing song. So we need to measure the amount of sound energy generated by this in 1 second, which means to say the total amount of energy that you can generate in 1 second. So this brings us to power. So during the production of sound, we are interested in the power of the device. Therefore, in preamps, preamplifiers, amplifiers, or even some of the drivers of sound, all right, they will give a rating in terms of power, which means to say how much you are able to generate the sound from these devices. Okay, now next, as the sound progresses, okay, sound will spread out in terms of area and other things. Okay, so let's go to the next one. Now, it's as if that it is a, imagine you dropped a drop of water onto a still water. The drop right at the center will produce a ripple. Now the ripple is actually energy produced by this thing. Alright, and the ripple will spread as it goes along. Which means to say that if the ripple is the energy, you are starting to spread the energy across as the wave travels. So as you can see, initially you may have what actually changes. Initially you may have a very high amplitude down here, but as the ripple spreads out, the amplitude gets lower. Alright? So which means to say that I could have, so I'm dripping it at says 1 joules per second for all the drops of water coming in. But the energy that I receive down here may not be 1 joules because this 1 joules of energy has been spread out across the rest. So during the propagations of sound, we are not interested in actually the power anymore. We are interested in the power of the energy in one unit area here. In one unit area here, how much energy am I receiving? So you got to take the power divide by the total overall area, and this gives you what we known as the intensity I of the sound, and it's measured in watts per meter square. All right, so this, and lastly, once it reaches the ear, your ear would have a particular area in the eardrum, and you receive that amount of energy, and it's translated to electrical pulses interpreted by the brain in terms of songs. So can you imagine? Energy will cover all the way from the production of sound to the propagations of sound and ends at where? And ends at the just before the perceptions of sound. Okay, let me give you a summary again. Okay, energy is like this amount of water that you have. In total, you can produce this amount of energy. Okay, but when you produce the thing, you would let the water flow out at a particular rate per second via a, say a tap. So this is the rate. So this would be the power, the amount of energy, water that flows out, the amount of energy that flows out. Okay, so as the water drips onto a surface, it starts to spread over an area inside here. All right. So if I want to find out how much energy per unit area I'm receiving at this end, then it will be intensity. Okay, this is drawn in terms of analogy. Okay, let's see how in actual fact sound actually produced. Okay, this is the sound that comes out from a speaker. Okay, this is the sound that comes out from the speaker. Now, the speaker is connected to an amplifier, an amp, and the amp is driving it at, let's say, 4 watt root mean square RMS to this speaker. So the speaker is producing, what is this, 4 watt, the power. Okay, maybe this amp draws from a battery, okay, of about say 4 kilojoules of energy, and it's draining at about 4 joules per second. So 4 kilojoules is 4,000 joules. Each second it drains 4 joules. So within 1,000 seconds, this battery will drain. Okay. Now, and it drives these things inside here. Now, at a distance of say 10 meters, when it's producing, this thing will be producing at 4 watt. But at distance 10 here, the 4 watt is distributed over the whole entire area here. So we are not interested because our eardrum or whatever, of our microphone or whatever receiving end, that's our eardrum, is only this amount of area. He's able to only capture this amount of sound that is generated from this whole entire sphere of sound. So we are not interested in overall power anymore. We need to divide the power over by the entire area of this sphere, giving us intensity, watt per unit area. So if we want to see how much energy that we are receiving or how much power we are receiving, we simply take this intensity and multiply by the area that we have receiving. And we're able to know that how much energy that we are receiving at this end. So you see, in production, we're interested in power. In propagation, we're only interested in intensity. Okay, but intensity, most of the measurement is not done in watt per meter square. All right, when you measure, majority of the time is given in dB. So what then is dB? Okay, so dB will cover in a short while. So for steady sound, the continuous flow of energy means that any increase in T makes a proportion increase in T. That means the longer you have, the more energy it spends, correct? I'm producing a 1 watt per second. My T is now 2 seconds. In total, I produce 2 joules. All right, so that's what. The longer we use or the longer we wait, the greater amount of accumulated energy. So remember, you have a water flow. The rate of flow of water is the power. But if you let the water run for 1 second and you let the water run for 2 seconds, this cumulated amount of water that's being flowed is equivalent or is analogous to energy. All right, so remember, power is the rate of energy flow. Then next, because you're flowing water across and it's dripping and the ripples spreads out over an area. Now at the receiving end, the water that's producing at the original source, all right, is spread over a large area. We're not interested in the overall area of the thing. We want to measure how much we're receiving at our end. So we need to divide the power by the area. That's why we get intensity is equals to power over area, where here the S here simply means area. Okay, now here's the good thing. See, energy intensity is equals to power over area. All right, okay, now power is equivalent to energy over time. So that's what it means. Now remember, energy is proportional to K, is equal to K amplitude squared. So which means to say that, hey, energy is proportional to the square of amplitude. Power is also proportional to amplitude square. And intensity is also proportional to amplitude square. So if you have some proportionality here and you have two values, therefore, if you have value first intensity 1 and the second intensity 2, then you can rewrite it's basically the amplitude of intensity 1 over the amplitude of intensity 2 squared. So this is where your indices comes in. Alright.